Okay, on to my fourth video. This is decision 1. This is the year 12 January internal assessment 2022. And I'm going through the decision paper here. So it's a 30-minute paper, so it shouldn't take me too long to go through this one. If you have any questions at the end, please either rewatch the video or come and find me if you're still stuck. But hopefully this will answer any grey areas or uncertainties that you have. Okay, question 1. 6 items with weights given in the table are to be packed into boxes, each of which has a capacity of 10 kilograms. Use the first fit algorithm to pack the items in the order given and state how many boxes are needed. All right, so it's first fit. So it's going to pick up an item and it's going to pack it into a box. So open up box number one, and I'm going to pack in A, which is worth 2. I then pick up B, that can fit in there because the capacities of these boxes are 10. I can pick up C and also dump it in there, so that's great. Pick up D, doesn't fit in there, so I've got to open up a second box. So box 2, D in there will have a 3. I can pick up E and that will also fit in there. I then pick up F, that won't go in box 1 or 2, so I've got to open up a third box and F will go there. So that's just the first fit algorithm. You're just picking up a box, the next box in the line, and fitting it in the first box that will fit in. Does state does ask how many boxes are required. So we need 3 boxes. Okay. Part B. Use the bubble sort algorithm. Okay, so it means you must use the bubble sort algorithm for this. To sort these items into descending order, you must state the order of the items at each pass. Okay, so you don't have to do all the little bits in between the passes, you just have to do each pass. So we're going to start with pass number 0, which is the original list. So 2, 1, 6, 3, 3, 5. Okay. At the end of pass 1, what's going to happen is we're going to go down the list and we're going to say, okay, do these need swapping, yes or no? And we want to pack it in descending order. So yes, they do swap, so the 1 will go up. The 2 and the 6, will they swap? No, so the 2 remains. The 6 and the 3, will they swap? Yes, so the 3 will go. The 3 and the 6, will they swap? Yes, so they'll go. And then the 5 and the 6, will they swap? Well, yes. So that'll go, oh no, that's ascending order. Start again, B1. Descending order, so the biggest on top. So do those 2 swap? No. Do those 2 swap? Yes. Do those 2 swap? That's the 1 and 3. Yes. 1 and 3 again will swap, and the 1 and 5 will swap. So that's what it will look like after the first pass. Apologies. Pass number 2, just repeat that, but you don't need to check the last one. We know the last one is correct. Do these need to swap? Yes. Do the 2 and 3 need to swap? Yes. Do the 2 and 3 need to swap? Yes. Do the 2 and the 5 need to swap? Yes. So therefore that's the second pass. Pass number 3. Those 2 are now locked in. We know that they're safe. Do these need to swap? No. Do those need to swap? Well, it won't actually make any difference. Do those 2 need to swap? Yes. And we know that these 2 are safe. Pass 4. These 3 are locked in. These 2, do they need to swap? No. Do these need to swap? Yes. Do these need to swap? Well, those are already locked in, so you need to check those. Now, we can see as humans that they are in the right order, but as part of the algorithm, you need to do the 5th pass because there was a swap made in the 4th pass. So therefore, you must do the 5th pass. But we can see they're already in order. So 6, 5, 3, 3, 2, 1. I have to see the 5th pass written down. But once that's done, you can stop. Okay, you have to complete the 5th pass. Okay, and then part C, apply the first fit decreasing algorithm to the items and state how many boxes are needed. So we're going to do exactly the same again, except this time we're going to pick up the biggest box first. So we're going to pick up C first, so that's going to go in the first box. Then we pick up F. That doesn't fit in box 1, so I'm going to open up box 2. Then one of the 3s, so D, that will fit in box 1. The other 3, which is E, that will go in box 2. The 2, which is A, that will go in box 2. It doesn't fit in box 1. And then finally B, which is 1, will fit in box 1. So therefore we require 2 boxes. So in this case, first fit decreasing gave a better solution than first fit. Okay, question number 2. Figure 2a shows a cube. Figure 2b shows the adjacency graph of the cube. State a Hamiltonian cycle of the graph. Okay, so Hamiltonian cycle is a cycle which visits every node exactly once and returns to the start. So there are many out there for this question, but the most obvious is, I think, starting at the top and just working way around. You must go back to the top. Okay, so top, back, right, bottom, base, left, front, and then you have to go to top. And that is a Hamiltonian cycle. There are many out there, but I think because of the way this one's laid out, that's the most obvious. Okay, B. Use the planarity algorithm to decide if the adjacency graph is planar or not. Okay, so it's already set out in a nice Hamiltonian cycle setup, so we can ready to do the planarity algorithm. So choose an arc. Let's choose top right, and we're going to put that outside, and then any that crosses must go inside. So this arc has been chosen. So left back then has to go inside, and base back also has to go inside. Okay, so those two have been chosen. I'm just going to do little crosses for the inside ones. You don't have to annotate this, but it helps to visualise it a bit better. Okay, any that those two have crossed. So we've got front base and front right. They have to go outside. So front base goes outside, and front right goes outside. Okay, then any that those cross has to go inside. So left top it's going to go inside. And then that's all the arcs labelled. So all labelled, no contradictions. Oops. Therefore, this graph is planar. So it's good to conclude. Therefore, this graph is planar. All right, there we go. That's not the only right answer. There are other ones, but you have to follow through the algorithm correctly. Okay, and finally question 3. A company is planning its production of M powder for the next 3 months. Over the next 3 months, 20 tonnes must be produced. Production quantities must not be decreasing, i.e. the amount produced in month 2 cannot be less than the amount produced in month 1, and the amount produced in month 3 cannot be less than the amount produced in month 2. No more than 12 tonnes can be produced in total in months 1 and 2, and production costs are £2,000 per month in month 1, £2,200 per month per tonne in month 2, and £2,500 per tonne in month 3. The company planner starts to formulate a linear programming problem to find a production plan which minimises the cost of production. And we can see the start of his work there. Part A, explain what the variables C, x1, x2 and x3 represent, and write down 2 more constraints to complete the formulation. Okay, so C is the cost of production. Okay, that's why it's been depicted with the letter C, because it's for cost. Xi is the number of tonnes produced of M powder really, produced in month I. Saves writing out 3 times, just use subscript I. So X1 is the number of tonnes produced in month 1, X2 is the number of tonnes produced in month 2, and X3 is the number of tonnes produced in month 3. Write down 2 more constraints to complete the formulation. Okay, so what have we got so far? We know that X1 plus X2 plus X3 is 20, so that's the first one here. Over the next 3 months, 20 tonnes is to be produced. Production quantities must not be decreasing, so the amount produced in month 2 cannot be less than the amount produced in month 1, so that's represented here. Amount produced in month 3 cannot be less than the amount produced in month 2, so that's not been represented. So that would look like X2 is less than or equal to X3. Okay. No more than 12 tonnes can be produced in total in months 1 and 2. So in total, X1 plus X2 cannot exceed 12. So those are the other 2 constraints then to complete the program. The bottom bullet point there is production cost, which feeds the objective function. And these 3 constraints are you cannot produce negative amounts in any month. Okay, you've got to be positive. So that's the complete program based on the information up here. The good news is that even if you couldn't extract the information from the text, you can still get full credit for this part because the linear program is given to you. It can be shown that the linear programming problem above can be reformulated. That essentially means altered in some way or another to this thing. And it's gone from a minimized problem to a maximized problem. And we notice that X3 has disappeared, which is necessary for this course because a graphical solution would have to be a 2-dimensional problem. Okay? You're not expected to solve a 3-dimensional problem graphically. What it's essentially done is it's made use of this equation to eliminate X3. So this equation as a constraint actually gives the feasible region here as being a 2-dimensional issue, a 2-dimensional region, but it's a 2-dimensional region in 3D space. So the reformulation has changed it from a 2-dimensional region in 3D space to a 2-dimensional region in 2D space. So that's more something that you're familiar with working with. Okay. The good news is you're not required to show this formulation. Okay. All right, use your graphical approach to solve this linear programming problem. Interpret your solution in terms of the company's production plan and give the minimum cost. Okay, right. So, first of all, let's just decide where these are going to cross the axes. So I'm going to put X1 on the X-axis and X2 on the Y-axis. So if X1 is 0, then X2 is 10. If X2 is 0, then X1 is 20. This one here is 12 in both cases. So I need to go up as far as 20 in X1 and 12 in X2. This is going to be necessary when I come to graph it, which is now. Right, so I need to find a ruler. Excuse me. Organised as ever. We'll go with it. Okay, so I need to go up as far as, what was it? X1 is 20 and X2 is 12. Okay, so 1, 2, 3, 4, 5. Let's have that as 20. And that is 0. You need to choose your scale. That's the thing with these questions. You will be given a blank bit of graph paper and you'll need to choose your own scale. You don't have to have the same scale on both axes either. Yes, it's 2, 4, 6, 8, 10, 12, 14, 16, 18 and 20. That's my scale down there. And I need to go up as far as 12 on my X, so probably double the scale. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's X2 going vertically up with X1 going that way. You could have them the other way around, that's fine. You don't have to have x1 on the horizontal and x2 on the vertical. You could swap them around. Okay, right. So I need to go from 12 to 12. Let me use this as my ruler. So 12 to 12. If you have an actual ruler, it might look a bit better. Just bear that in mind. There we go. 12 to 12. 10 to 20. So 10 on my vertical to 20 on my horizontal. There to there. And then I've also got the x1 is less than x2. So it's going to be, on my scale, it's going to look like a gradient of 2. Good. 10 goes that way. Okay, you decide which side of the lines you are shading. So I need x1 to be less than or equal to x2, so I'm going to shade this side of the line, and the shading like this is perfect. x1 plus x2 is less than or equal to 12, so the origin satisfies that, so you get rid of the top end. And what's it, x1 plus 2x2 is less than or equal to 20, gets rid of that there. So that's my graph. This here is my feasible region. I mean, I've also got x1 and x2 are both positive, so I could shade the back end of that axis there. So that gives me these points. So I've got a point up there, a point there.